Welcome to our lesson on the power rule. So in a previous lesson we've just sort of defined this term derivative. The derivative of f at x was defined as f prime at x is equal to the limit as h goes to 0 of f at x plus h minus f at x all over h. So right now when I ask you to find a derivative, so let's say the function was f at x equals x. The only way you have to do that is to put this, into this limit definition. So f prime at x equals the limit as h goes to 0 of f at x plus h, which in this case f at x is, I'll write it down. No, I won't. Yes, I will. Minus f at x all over h, and then I have to use f at x, which is just equal to x. So that would be x plus h plus, this is the limit as h goes to 0, f plus h minus f at x, which is just x, all over h. These x's cancel out. So we've got h over h, which is just equal to the limit as h goes to 0 of 1, which is equal to 1. So the derivative of this thing is equal to 1. And then, let's say second example, f at x. This is example 2. Equals x squared. So f prime, I think we did this example this might have been like our first example when we did the definition. So here you're going to have to do f at x plus h, so that would be x plus h squared minus x squared all over h. And if you remember what happens, you're going to have to square this bracket, and your x is going to cancel out. I won't write all the calculations out, I'll leave that to you, but you end up with 2x. And now let's say I give you a third example, and again I'm going to ask you to do this one on your own. F at x equals just x cubed. So here f prime is going to equal the limit as x goes to, h goes to 0 of x plus h cubed minus x to the 4 all over h. And to check your answer, this one ends up being 3x to the 4. Once you do the limit, and how are you going to do the limit? Well, you're going to have to expand this cubic, and then, this wasn't cube, this was to the 3. Expand the cubic, and then you end up with things canceling out. You end up being able to reduce the h, and you end up with just this answer here. And you can imagine, okay, so we did x squared, x cubed. If I asked you to x to the 4, you could do that. It would just be, this would become a fourth, a power of 4, so you'd have to expand something to the power of 4. So, it would just involve doing larger and larger powers. So what you're going to find is, wouldn't it be nice if we had some way to evaluate derivatives without always having to use that limit definition? So notice, we just did a couple, right? D by dx of x was equal to 1. D by dx of, and I think I just told you, but you should have done this one on your own, was 2x. D by dx of x cubed was this one I just told you. You might start to notice a pattern. D by dx of x to the 4. Turns out, if you don't trust me, you can check it on your own using the limit definition. Turns out to be that. So maybe you start to notice the pattern that, okay, the coefficient here looks like it's just the power here. And what's happening to the power on this? Remember, that's power of 1. That was 1. The power seems to be dropping by 1 each time, right? Even in this case, right? What's the power really here? It's really x to the 0, which is 1. So it appears that we maybe could generalize that as a rule that if n is an integer, then the derivative of x to the power of n. So that's just what we're doing over here. N was 1, 2, 3, 4. It looks like it's just n becomes the coefficient, and then x to the power of n minus 1. So, and this turns out to be true. This is what we call the power rule. I'm not going to prove it for you in this video. Really, the way you prove it, so we'll proof in later in other videos. So I'll put a proof just of the proof of the power rule, and you can watch that if necessary in other video. And this actually turns out to not just be for integers, this turns out to be for any number, for any real number. Although it's a little bit trickier to prove for any real number than any integer. Okay, so let's just do some examples to see how this works. Okay, so this rule that we had stated, it also works, and I think I mentioned that it works for any real number, not just integers. So let's look at some examples of what I mean by that. So any real number means, well, let's do another integer. It works for negative numbers too. So let's say f of x is 1 over x cubed, and you want to find f prime. Then just think of f of x as, remember, that's equal to x to the power of negative 3. So the same rule is going to apply. N will be the integer, or the exponent will become a coefficient, so negative 3 x to the power of, and then this will decrease by 1. So 1 less than negative 3 is negative 4. So it's that, and then oftentimes you'll write that as negative 3 over x to the 4, so with a positive exponent. But it'll also allow us to do ones like this, so you might be looking at that saying, well, where's the power? Just remember that a square root is really the same as to the power of a half, and this is not an integer, but it is a real number, so as we said, it works for real numbers. So dy by dx, remember the exponent will become our coefficient, x to the power of, and then 1/2 minus 1 would be negative a half, so negative a half. And then oftentimes you'll write that as 1 over 2 times, so negative a half means it's in the denominator, so x to the half, or 1 over 2, and then x to the half is really just root x. So the derivative of square root x is equal to 1 over 2 square root x. And just one more, so kind of strange function, f of x equals x to the power of square root 2. Well, root 2 is a real number, so you can apply the power rule. So root 2, the exponent, will become our coefficient, x to the power of, and then this decreases by 1. So that would just be root 2 minus 1, and I can't do much with that, right? Root 2 minus 1, you can't simplify that very much. So that's the derivative. So just doing that to kind of show you it works for fractions, it works for square root numbers, any real number.